So in the previous few lessons, we have been talking about some special types of relations. We have already talked about reflexive and symmetric relation. Today, we are going to talk about anti-symmetric relations in this video. So before we move on and see the mathematical definition, what you need to see is an example. Very simple one. Suppose there's any person P and we are saying that the person is related to Q provided P is not taller than Q. Now, if you are thinking about symmetric relations, you know that Q should be related to P as well. But under this relation, is it possible? If you just think about the basic understanding of this height, you will actually see that this is possible only when they have the same height. So none of them is taller than the other one. So this is basically the essence of an antisymmetric relation. Mathematically speaking, suppose this is the relation, you take any pair of the form A comma B and also the inverse pair is present, the only obvious consequence should be A and B are equal. In other words, if you find any pair where A and B are not equal, if one of the pairs is present, then the inverse pair cannot be present. So let's take an example. Suppose I'm considering any set A, which is having three elements P, Q, and R. And basically, this is capital R, which is a relation on the set A, having these many elements. Okay, so these are the ordered pairs. What have we said here? We are going to judge the elements that are having basically different first and second components. So I'm going to judge PR and QR. For PR, we need to check whether R comma P is present or not. The point is it's not present. Similarly, for Q comma R, we don't have R comma Q. So definitely it's an antisymmetric relation. So the second thing that we are going to learn here is the matrix representation. So this is something we have also done for reflexive and symmetric relation. What we are going to do is form a matrix having entries based on the presence of the particular ordered pair. So we are actually writing 1 if this is present, otherwise it's 0. For reflexive relation, we talk about the diagonal. But for symmetric relation, we have talked about the off-diagonal entries, the mirror images. Here, we are basically going to do the same thing, which is like 0, 0, 0, 1, and 0, 1. So for antisymmetric relation, what you are going to notice is you cannot have two ones simultaneously. It can be 0, 0 or it can be 0, 1, 1, 0. You cannot have one for both the cases. Now, it might look from the definition that it is kind of opposite to symmetry. So think about the fact whether antisymmetry is the opposite of symmetry or not. So I'm going to actually answer that question. But before that, let's go ahead and do some examples. So I'm going to take a very simple set A having three elements x1, x2, x3 and take some examples of relation on that set. Starting with the first example, R1. Now you can see that there's no such pair having first and second component different. So we are not even going to judge this. This is antisymmetric. Again, if you take the second pair, you will see that basically you have x1, x2 and x2, x1. Both of them are present. So this is not antisymmetric. For the third one, again, you will see some problems, right? If you see this, you have x1, x3, as well as x3, x1. So this is not antisymmetric. And for the final one that we have taken here, you can check that there's no such pair having the first and second component different, but having the inverse pair as well. So this is perfectly okay. Now, if you have to check whether a particular relation is antisymmetric or not, you have to check each and everything, okay? So each and every possible pair where A and B are different. But if you want to prove something not antisymmetric, you can just find out one pair and that's it. Now, if you look at the first example, this is something very interesting. If you look at the first example, apart from being antisymmetric, this is also symmetric. So, in fact, look at the third example. This is not antisymmetric as we have already established, but this is not symmetric as well because clearly see that we have x1, x2, but the inverse pair x2, x1 is absent. So you can have actually relations which are neither antisymmetric nor symmetric. In fact, you can have relations where both of them coexist. So basically, they're not opposite in the sense that the absence of one will guarantee the presence of the other. Now that we have seen some examples in the roster form, let's go ahead and see some example in the basic set builder form. Now I've taken a relation R on the set of all real numbers, and it's defined by A is related to another element B provided A is less than equals to B. So what is the general procedure here? Always remember the general procedure for any possible property of a relation. What we are going to do is we are going to take A comma B as well as the inverse pair B comma A. Now we have to prove that A and B are equal. Before that, let's just explore the definition of the relation. So A is less than equals to B and B is less than equals to A. If you algebraically manipulate this, you will understand that together they only have one consequence, that A and B are going to be the same. So obviously this is an antisymmetric relation. All right, so let's take another example here. I have taken a collection C of sets, and we are saying that one set is related to the other if it's a subset of the second one. So if A and B are related, which is like A is a subset of B, and similarly B and A are related, which is like B is a subset of A, you know that the obvious consequence is A equals to B. In fact, in set theory, we have used this both-sided relation to prove equality of sets. So this is basically antisymmetric. Now, I hope from this video you understand the basic things about antisymmetry, you know the definition and matrix representation, and also how to check this for roster as well as set builder form. So practice these things. In the next video, we are going to talk about another special type of relation called the transitive relation. So stay tuned.